Hi everyone, I apologize if this is a bit haphazard. This talk was originally going to be half its content, and then that changed a couple hours ago, so bear with me. So I'll be talking about optimizations about RCI, and just going to start off with a beautiful dependency graph of NALU. Just imagine a situation where you have a constraint, and the constraint is you can only use exactly what you ask for in terms of resources to compile this entire graph. And if you need to make any changes to dependencies or variants or compilers, you have to stick with your original requests. Obviously, this doesn't work, but that's the current way we're doing it, and I'll talk about why and what we can do to change that. So if you have an example CI pipeline, and for more details on spack-CI, you can see Ryan's talk. But let's say you have 4 packages that you want to build, and I have a pretty good understanding of how many cores and how much memory I'm going to need to actually compile those packages. That information would get sent to a scheduler. And in an ideal situation, we might have 2 nodes that we have on AWS, very minimal waste. We use exactly what we ask for. Unfortunately, what we see a lot of the time is bad allocations. So, for example, a Trilinos build might ask for way too much and end up wasting a good amount of that. Same for HDF, 5, or any of these other packages. So that's kind of what we're seeing and what we actually want in reality. So current allocations are quite inefficient. If you have an over-allocation, like this example with Trilinos, it asked for 12 gigs of RAM, and it used just under half that for the entire lifetime of its build. On the other hand, you can have the opposite of that, where you ask for far too little, and you are using way too much of that, which can cause resource contention. You get kills, and the opportunity cost of someone's build, on the other hand, working correctly. So you kind of have these 2 sides of the coin where you have good amount of waste and waste in another sense that I think we can fix. So the bottom line is that most jobs are underutilizing their allocated resources. Here's this histogram of individual package builds for each package that we build in CI, and the ratio of a package's resource usage or RAM usage over its request. And as you can see, the vast majority of these packages are using hardly anything of what they request. And then you have these ridiculous packages that are using like 500%. So the bottom line is that 13% of allocated memory is actually used on average during the lifetime of CI jobs, which I think is something that we can definitely improve upon. So what we're seeing is this top situation where we're seeing waste and we're seeing opportunities for optimization, which means better packed instances on AWS and potentially better right-sized resource requests. So the idea is that we have all these executions are running 20,000 times a week. We control each one of them, we provision each one of them, and they're quite predictable. Cycles, money, and time are being left on the table with these pretty inefficient allocation decisions, and we can leverage our control of the CI infrastructure to take these findings and turn into production value that can help our users save time and our project save cycles in AWS and just efficiency in general. So the good thing is that package attributes are actually quite good predictors of usage. If you have a package's version, its compiler, and its build options, variants, and you put that in a very, very simple model that takes the past 5 builds, conditioned on these package attributes, you get a pretty good prediction of how much memory and how many cores are going to be consumed on average during the lifetime of a CI job. And the idea is that once PRs are added, once additional package updates are created, if you have a change in your stack that you're trying to build in CI, and if you have build failures, basically any change that happens within the ecosystem of the CI, we want that to influence what the prediction is going to be in the future so that we can see this sort of feedback loop occurring within the CI. So just to give some top-line numbers, the memory allocation error, if we use these past 5 builds, you see a pretty substantial reduction. So the current allocation strategy is we're seeing about 3.2 gigabytes of waste per package build. We're able to reduce that on average to around 114 megabytes, which is quite good. And on the CPU side, we're seeing a far smaller reduction, but it's still pretty good. Reduction of about 2 times. However, there are some problems here that complicate what we're trying to do. We want to avoid poor utilization, which I think we've established is happening. We want to potentially increase the throughput of the CI because, as I'm sure many of you are aware, we're not building every single package that gets submitted in a PR. We're building a subset of packages that we've previously defined in our stacks that we are aware or that we are confident that we have the resources to build. We also want to lower the cost per job. If we are going to ultimately build every single package in CI, we want to make that sustainable, and we also want to be a good steward of the credits that we've been provided by AWS. And at the end of the day, any of these modifications have to enhance the stability of the CI. We don't want a situation where we're reducing the amount of memory or we're throttling the amount of CPU that a build is getting and end up denigrating the user and developer experience. We want faster throughput for PRs and for users in general. So I'm going to talk a bit about how we've taken some steps to make sure that we are going to engage stakeholders to anticipate any of these challenges, and a little bit about some of the safeguards we've had to implement. So the way that this works is every single time a package build completes in GitLab, that gets sent to an online service, and then we collect metadata about that job in GitLab, which has the abstract spec for the package and resource information for that build in Prometheus. We have second level granularity when it comes to CPU and memory usage. That gets put in a job database. We have the package metadata, we have the resource usage, whether the job failed and the reason for that failure, and information about the AWS instance where that job was compiled. So we have the target and we have the processor of that build. And I'll talk a little bit later about how we're measuring costs, but that's also something that we're measuring here. So in terms of how this will be integrated into the production environment, you submit a PR, and if that PR is in the list of packages that we are building within CI, that gets sent to the spack-gantry service. We check the historical metadata and resource usage, and that gets outputted as a prediction. So just to take a quick step back about how this is currently working, we essentially have different buckets, different levels of resource intensity that we are basically assuming about different specs. So Trilinos, HDF5, OpenMPI, those might be in the higher level bucket, and that's why we're seeing such high waste when it comes to these allocation decisions. But I don't think it's really reasonable for someone to have to go in and measure the expected resource usage of a job when the combinatorial nature of SPAC makes it possible to have thousands and thousands of options that we can potentially build. And that would explode if we ever went to a system where everything got built. So that's just the background of why this is necessary and why what we're doing about it. So after that prediction is getting sent over to GitLab, that gets sent to the orchestration system, which is a combination of Carpenter that essentially allows us to pick relatively affordable instances on AWS spot instances, and that's all running in a Kubernetes cluster. So I want to talk a bit about what success might look like, because there are some competing factors when it comes to utilization, throughput, and cost. So the future direction that we're ultimately looking at taking this after we add the proper allocation decisions into the CI is creating a scaling experiment. And a lot of this ties into what Kathleen was talking about earlier today about how to allocate the appropriate amount of resources to a job. And that's mostly on your local system, but this is, I think, applicable to CI and also what she was talking about. So what would happen if we fuzzed the resources provided to a build job? You might assume that in all cases a make J8 is faster than a make J4, but we have the opportunity to manipulate every single component, every single input into the build system, and we can figure out which one might be cheaper. So the goal essentially is to experiment with about 10 to 15% of builds and incorporate any findings into allocation. So just talking about what this actually looks like, we can manipulate the amount of threads that are allocated to a build job. We can basically choose the instance that job is running on, and we can basically figure out, does it make it faster to run on a newer, more expensive chip, or is it worth it to potentially have a slowdown in the build time and keep it in a cheaper instance? In addition to basically figuring out what the optimal balance between the threads that are being provided to a job and the make jobs. So about cost, we want to be a responsible cloud user. And just to give an idea of how this is currently working, we have AWS spot instances. They offer a cost per hour that we are charged for every hour you use the instance. And this is just an assumption, but for the purposes of this formula, I'm assuming that CPU and RAM represent half the cost of an instance. And then each instance has a unit of RAM and CPU associated with it, and we can essentially see what the cost of a single CPU unit and a single memory of RAM is for the lifetime of an instance. So the crude metric that I started with was looking at the CPU usage. So that's a pretty basic way of saying, okay, how much does it actually cost to run this job in CI? But the problem with just taking the usage is, we understand what we're using, but that doesn't really solve or doesn't really optimize for the initial problem that we saw earlier, which is we're seeing misallocations happen. So jobs should be penalized for how much they're misallocating. We should encourage the jobs to not over or under allocate by charging an artificial cost. And while this is not necessarily a cost in an accounting sense, but it adds a penalty for how much the job actually consumed, either from the opportunity cost of another job not having access to those resources, or from the cost of resource contention that happens when a job is using far more than it expected, which can cause contention on other jobs within that instance. So that's the idea behind this, and I think what's good about this formula is that it optimizes for a number of things. Because we have the cost of a CPU and of a unit of CPU and a unit of memory for the lifetime of an instance, you are optimizing not only for the time, the wall clock of a compile, you're optimizing for an appropriate allocation, and you are also optimizing for the usage of each unit of memory and of CPU, which would help if we are going to do the scaling study where we try to pick the most appropriate instance for each job. What we also want to do is investigate approaches to scheduling jobs. So the current way we're doing it is through Carpenter, where you could potentially spin up an entire instance for one job if you have nothing else ready to go. So we don't really want to get charged for an entire instance if it's only going to get used for one job. So we could look at implementing a queuing system for this, and also picking jobs with similar build times on a single AWS instance, so they're all running in parallel, so there's not this inconsistency with 10 jobs taking 5 minutes to run, and then another job taking like an hour to run, and then you have all these wasted resources just on the node with nothing else to run on. So we're looking at doing these in a custom Kubernetes scheduler, or looking at cloud batch solutions like AWS Parallel Cluster. That's it. The infrastructure code for the collection and for the prediction is all available on GitHub, and you can reach out to me or Alec, as we're both actively involved in the project. Thank you.
Thank you, Caetano. We do have some time for some questions, I see. Hi, nice talk, thanks. So one of the problems, for example, some time ago there was a update to Clang, and which increased the memory consumption of all builds by 15% or 20%. And in such cases, the prediction might go wrong and all the builds might start failing. And then what would be the recovering plan from there? How would you deal with it?
Sorry, can you repeat what you said the error was, or what the issue was?
Clang, so
And
changed and now it consumes more memory, so all your builds are going to fail.
Okay, well, yeah, that is something I didn't get to, but the idea is that when we hit an issue with the resources needing to be scaled up quite quickly, if it gets killed, the idea is that once that is detected, we basically drop any resource restrictions, and then it would learn that for the next time it needs to run, it needs 20 times more memory, and then it would not get killed again. So that's the safeguard that we're looking at implementing for that sort of situation.
okay, other questions?
So I'll ask the flip question. So let's say we blow past the memory limits and then the LLVM developers realize, oh crap, we introduced a bug that blew up our compilation memory usage, and now the next one uses 10% of the memory usage. What mechanism gets it back down in the long run?
Well, yeah, so the idea is for that safeguard, it only lasts for like 5 runs, and then it checks what the usage was for the past runs, and if it needs to go down, it'll go down again. So it's just a feedback loop that will be constantly running to see what the updated allocations need to be.
So in terms of the plans of growth of this, is this intended to be implemented as a SPAC CI only type feature, or is this something we might expose to the user base? And I ask that because we essentially would like to tackle the same problem for our own builds, and we would also like to integrate these type of heuristics potentially into the job server directly as well for some of our larger, more complicated builds.
Yeah, so luckily that's the way we've designed it. Essentially, it's an API that you provide an abstract spec to. It tells you what you should expect to need to compile your job. And we're looking at in the future if you need to provide a certain target or any other constraint that should be able to provide you predicted resources. So that should work for that use case.
Any other questions?
Yeah, so I'm coming from Phil's group as well, which I see this being more broadly usable than just doing SPAC build approaches, right? So for one thing I notice is I think the assumption here is you have unlimited resource pool. They're just expensive and you want to minimize cost. We have our own resource pool internally that is size restricted, and it seems to me like you could tweak the reward functions, et cetera, to have it maximize throughput for a group of users on a fixed set of hardware instead of just minimizing cost. Yeah. So this is really interesting. I'm happy to see this being done.
Okay, one more question on this.
Hi. Maybe simple. Let's say you had a package where there's an expensive link step at the end, so consumes, let's say, 4 gigs of RAM 90% of the time, then it spikes and wants 50. What is Gantry going to allocate in a situation like that?
Yeah, so I didn't really talk about the distinction between requests and limits yet, but most of this presentation was about a soft request guaranteed to that job. So if you see like a situation where the mean is quite low and then you have a spike at the end, the idea is that we would also sort of train it on the peak usage of all these packages and set that as the memory limit. So that would ideally not be an issue, but if it does get killed, the feedback loop would help that out.
All right, thank you, Caetano.